Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson number 2 on slope and perpendicularity. Now remember, Unit number 5 is all about learning the tools of coordinate geometry that we will be using to prove things and to solve other problems, all right? In the last lesson, we looked at how the slope of a line or a line segment related to two lines being parallel to one another. And it was an easy relationship. Two lines will be parallel if they have the same slope, and if they have the same slope, they'll be parallel. All right? Yeah, well, whatever. So it's an equivalence thing. Equal slopes means parallel, basically. Today, we're going to look at the relationship that occurs between the slopes of lines that form 90-degree angles with one another. And of course, those are critical when you look at right triangles, rectangles, squares, and a variety of other geometric figures. So let's jump right into it, and let's see if we can discover that relationship. All right. Now in exercise 1, what we've got is we've got two graphs, okay? And in both situations, I've drawn line segments that are perpendicular to each other. And what I'd like to do is I'd like to just graphically determine the slopes of all the line segments involved, okay? So what I say we do is we do the first slope of letter A together and then have you do all the rest of the slopes on your own. So let's jump into it. Exercise number 1. In the following two diagrams, two perpendicular line segments have been given. Letter A, determine the slopes of both line segments in both graphs. Label each slope. All right, so together, let's talk about line segment AB and find its slope graphically. Remember, slope, right, will be rise divided by run, the ratio of rise to run. So if we look at line segment AB and we pull off that point, and then we look for another one that's nice, and maybe another one that's nice, etc., right? They don't have to be nice points, but nice points are nice, if you know what I mean, right? What we see is that we run 3 units for a rise of 2 units every time. So for AB, I would say that the slope is 2/3. And actually, let's do CD together as well. All right, and the reason that I want to talk about CD, right, is that CD you should immediately look at and say, as we read this graph moving left to right, CD is going down, and therefore it has to have a negative slope to it, a negative slope. Now with the slope formula, you don't have to worry about that whole y2 minus y1 divided by x2 minus x1. Plenty of practice with that today. You don't have to worry about positive, negative, it'll come out in the calculation. When you're doing it graphically, you literally have to look at CD and go, well, that thing is going down, therefore it has a negative slope. Let's take a look at CD. Same kind of idea. Try to find some nice points. There's a nice one, a nice one, a nice one, etc. All right. And what I see is that for every 2 units that it runs, it actually falls 3 units. So the slope of CD will be negative 3/2. So the slope of AB is positive 2/3, and the slope of CD is negative 3/2. All right, why don't you go ahead and do the 2 slopes from this particular graph. Pause the video and take as much time as you need. All right, let's go through them. And maybe what I'll do is I'll work them out kind of up top here, and then we'll put them down in the results down here. Let's take a look at line segment EF, okay? Nice point, nice point, nice point, nice point, etc. All right, and what I'm seeing is that for every 2 units that I'm running, I'm rising 1 unit, all right? So for EF, it appears that the slope will be a rise of 1 for a run of 2. Now, just like before, GH, okay, certainly looks like it's got a negative slope. Doesn't just look like it, it does. Now, a little bit trickier, for every run of 1, it's dropping 2. So for GH, right, its slope will be -2 over 1. Or just negative 2, but I like to keep it as negative 2 over 1 for right now to see this relationship. So let me bring these up and write them right down here so that we can compare, contrast, etc. For EF, we see a slope of positive 1/2, and for GH, we have a slope of negative 2 over 1, or just negative 2. All right. Now what we'd like to do is see if we can kind of deduce a pattern here. All right. Letter B says, list as many observations as you can about the slopes of these perpendicular lines. All right. Now again, what I want you to do is kind of compare these, think about them, compare these, think about them, and write down anything you can. Take a few moments. All right. Well, hopefully one thing is pretty obvious. Let me extend the page a bit. Bring it back down. So observation 1 that I would make is one slope is positive and one negative. Or you could say they have opposite signs, right? And that will always be true as long as you don't have vertical or horizontal lines. Two lines will be perpendicular. Well, one of them, if it's got a positive slope, the other one's got to have a negative slope. There's just no getting around that, right? If one of them's going up, the other one has to go down. The other observation is a little bit trickier, especially like trickier to kind of verbalize. But notice, forgetting about the negative for a second, 2/3 and 3/2. 1/2 and 2/1, or 1 over 2, 2 over 1, 2 over 3, 3 over 2, okay? They are, the fancy term is reciprocals. Actually, they aren't reciprocals of one another, but their absolute values are. All right, reciprocals are numbers like, let's say, 4/3 and 3/4, 7/2 and 2/7, right? It's when you take a fraction and you flip it, so to speak. So altogether, though, right, altogether, we can summarize this in the following slide. Okay? Two perpendicular lines that are neither vertical nor horizontal, and when we have our lesson on vertical and horizontal lines, it'll make a lot more sense why I gotta keep putting this in. But for right now, two lines that are neither horizontal nor vertical, that are perpendicular, will have slopes that are negative reciprocals of one another. Negative reciprocals of one another. So for instance, if I've got this red line segment, let's say its slope was 2/5. Then this blue line segment that's perpendicular to it would have a slope of negative 5/2. Okay? Some math teachers will give you another test. They'll say that two lines are perpendicular if the product of their slopes is equal to -1, right? Notice all of those kind of cancel out. And that's absolutely true. It was true in the first case where we had I think a slope of 2/3 times a slope of -3/2. That equals -1. Even when we had a slope of 1/2 and a slope of -2, that has a product of -1. But the technical wording on it is that two lines will be perpendicular if their slopes are negative reciprocals of one another. All right. Now that's a much more difficult relationship than what we saw with parallel lines, which is, hey, if they're parallel, they have the same slope. Okay. But perpendicularity is about those lines having about as opposite slopes as they can be, if you think about it. Now you don't want to say it that way. You don't want to say, oh, if they have opposite slopes, because the word opposite in math is a very loaded term. You know, if I said, hey, what's the opposite of 5? You might say -5, or you might say 1/5. Right? But basically negative reciprocals means that if one's negative, one's positive, and if one is 2/3, the other one is -3/2. All right? So now let's use this relationship for the rest of the lesson to both do some problem solving and a little bit of what's called coordinate geometry proof. All right, let's do it. Okay. Exercise number 2. Line segment AB has endpoints of -3, 7 and 3, 15. Which of the following would be the slope of a line perpendicular to AB? Okay. Now, you know everything you need to know to solve this problem now, so I'd like you to take a few minutes and take a shot at it. Okay, well, let's work on it. We know that any line that is perpendicular to AB will have a slope that is the negative reciprocal of the slope of AB. So the first thing that we should probably do is figure out the slope of AB. Let's do that. All right. So for AB, I'm going to use the slope, and since this is the first time that we're doing this in this lesson, let me just remind you of the classic slope formula. y2 minus y1 divided by x2 minus x1. Really just the change in the rise, the rise divided by the run, the change in y divided by the change in x. Remember as well, it doesn't matter which one you call x1 y1 and x2 y2, but I'll probably always stick with the first one being x1 y1 and the second one being x2 y2. So for AB, whoops, let me move that m a little bit farther down. For AB, I can say that the slope is 15 minus 7 in the numerator. Watch out in the denominator, that's going to be 3 minus a -3. So we'll have 8/6 in the numerator, and it's always a good idea when you can reduce a slope to reduce a slope. So the slope of AB is 4/3. Now, as always, if you're doing a multiple choice question, be very, very careful about getting a result and thinking, I'm done. Right? Hey, I got 4/3, the answer is number 1. But the answer is not number 1. That's the slope of AB. But the slope then that would be perpendicular to AB, well, not the slope, but the line segment, right, would be the reciprocal of 4/3, which is 3/4, and the negative reciprocal. So that's choice 2. All right, a very straightforward problem that requires 2 pieces of knowledge. Piece number 1, how do you calculate the slope of AB? And piece number 2, what is the relationship of that slope, 4/3, with the slope of a line segment perpendicular to it? Negative reciprocals. Well, not hard, right? You just gotta take those 2 pieces of information together and work through the problem. Take a moment now, if you need to write down any part of this problem. All right, let's move on. Okay, slightly more challenging, but we've got a graph. Let's take a look. Exercise number 3. If a line was drawn through point C in the diagram such that it is perpendicular to AB, at what coordinate point would the 2 lines intersect? So we've got this nice line segment AB, and we've got point C. I'd like to draw a line that goes through point C that is perpendicular to AB, and I want to know the point where the 2 intersect. Okay, so again, this is challenging, but you have everything you need in order to be able to do this problem. And in those situations, I like to take a moment and let you work on it. So go ahead and do so. All right, let's go through it. Well, what I'd like to do is I'd like to plot that line. I'd like to actually plot the line that goes through C that's perpendicular to AB. But in that case, I'd like to know what the slope of AB is, again, just like the last problem. So let's do that. Now, in this case, you could find the slope of AB graphically, or you could find it algebraically. It's up to you. Since I've got the graph just sitting here, I think I'm going to do it graphically. So there's a nice point, a good point, a good point, a good point, etc. And it looks like the slope of AB is going to be a rise of 2 divided by a run of 3. Now, what this tells me, though, is that the line that goes through point C will have to have a slope of -3/2, meaning that it will have to fall, I'm still going to call it a rise, by -3 and a run of 2. So let's plot some points, okay? Specifically, let's go over to point C and let's go over 2 and down 3. And over 2 and down 3. Now, in a certain sense, this is a little bit unfortunate because it's going in the opposite direction that we want to. But of course, we can interpret negative 3/2 as being negative 3 divided by 2, but we could also interpret it as 3 divided by negative 2. Remember, a positive divided by a negative divided by a positive are both negative. In that case, what I'm going to do is I'm going to go to the left 2 and up 3. And I know you've done this before when you've plotted lines. And now what I can actually do is I can go ahead and plot the line. I think I'm going to do that. You can probably already see where the intersection is occurring, but let's get the line itself. There it is. And it's kind of nice too, because if you plot the line in it, to me it's fairly obvious now that perpendicularity. And of course the intersection point is right here. So what are those coordinates? Looks like negative 3, 3. Just making sure, you bet. Negative 3, 3. That point right there. All right, so again, it kind of ties everything together, right? How do we find the slope of a line graphically? What is then the relationship between two lines that are perpendicular, or what's the relationship between their slopes, right? And then of course, what's an intersection point? None of this did we have to do algebraically. We didn't have to set up any equation or anything like that. We just had to be able to plot that perpendicular line. All right, let me step back for a second. Take a few moments with this if you need to, and then we'll move on to the next problem. All right, let's do it. Okay, now we're getting into the realm of what's called coordinate geometry proof. Okay, we looked at this a little bit with our parallel line work, and we're going to see it a lot more in the coming units because we want to be able to prove things not just using sort of like the Euclidean proof, you know, with side angle, all that stuff, but we also want to be able to prove things with hard, solid numbers, and that's where coordinate geometry comes in. So let's take a look at exercise number 4. Given the points A, B, C, and D, I'll let you kind of read off their coordinates for yourself, is AB perpendicular to CD? Provide numerical evidence. All right. Well, when we look at the picture, it certainly looks like it's possible that AB is perpendicular to CD. But the ultimate test is not whether it looks like the two segments are perpendicular, but whether or not their slopes are negative reciprocals. So what I'd like you to do is take a few minutes to calculate the slope of AB and to calculate the slope of CD, make the comparison, and then make the call. Are they perpendicular? Take a little bit of time. Okay, let's go through it. I'm going to go just straight up with the slope formula. Now, you do have the graph sitting there. You could possibly do it graphically, but let's do AB, right? For its slope, we'll do 4 minus negative 5, all divided by 1 minus negative 2. Okay, in the numerator, that leaves me with 9, and in the denominator, it leaves me with 3. And I can reduce that to 3, or I can reduce it to 3 over 1. I think I'm going to reduce it to 3 over 1 because I'm looking for that negative reciprocal business. So having the slope written as a fraction as opposed to a whole number is helpful, at least in this context. Let's now go through CD. All right. For CD, my slope is going to be 4 minus 6, all divided by 5 minus negative 3. Watch those double negatives. 4 minus 6 is negative 2. 5 minus negative 3 is positive 8. Again, it pays to reduce, and we get negative 1/4. So are they perpendicular to each other? And the answer is no. No. Why? Because the slopes are not negative reciprocals. By the way, this is a very, very common way to sort of abbreviate that phrase, negative reciprocals. You could certainly do it. Again, if your teacher would like you to use that idea of the product being equal to -1, you could do that. For instance, if I actually did the product of these two slopes, it would be -3/4, which obviously is not equal to -1. All right, but I'm going to pretty much primarily stick with the idea of being able to recognize whether two numbers are negative reciprocals of one another, and they're not. By the way, they're pretty close. Just for the record, they're pretty close. Had this thing turned out to be -1/3, which is obviously a fraction very close to -1/4, then they would have been perpendicular. And that's why they look very close to it up here. They look close to it because their slopes are close to being negative reciprocals. They just aren't quite. Whoops. So let's get rid of that. All right. Let's do one more problem. The last piece is to determine whether or not a particular triangle is a right triangle, right? So in exercise number 5, it says in triangle ABC, A is -5, -7, B is 7, -3, C is 4, 6, is ABC a right triangle? Justify. Use of the grid is optional, but advised, okay? You'll see that terminology on a lot of standardized exams where they give you a piece of graph paper within a problem and they say, well, you can use the graph paper if you want, but you don't have to. It's almost always the case that if they've given you graph paper, then it's a good idea to use it, but it's not absolutely necessary. Okay, now I assume you can plot these things, okay, but pause the video now, take a couple minutes, and plot that right triangle. Oh, I'm sorry, plot that triangle. We're trying to determine if it's a right triangle. Do you have it plotted? Because I'm just going to make it magically appear. Well, I was going to make it magically appear. There it is. All right, anyway, there's my triangle. Okay, and I'm trying to determine whether it's a right triangle. Now let's talk about why the use of the grid is optional but advised. Okay, this triangle certainly looks like it could be a right triangle. But if it is a right triangle, the only way that's going to happen is if this angle is a right angle. There's no way that that's a right angle or that's a right angle. So if my plotting is correct, if I haven't made a mistake in my plotting, then really what I want to see is whether or not this line segment, which is AB, is perpendicular to this line segment, which is BC. Okay, that's what I'm trying to do. So I can lessen my work. Could I also calculate the slope of line segment AC? Sure, I could. And in some situations, we're going to want all three slopes. But here, let's just do the slope. Let's just do the slope of AB. And let's do the slope of BC. All right. Why don't you take a few minutes, calculate those two slopes, then make your decision about whether or not this is a right triangle. Okay, let's go through it. Here we go. AB. -3 minus -7, all divided by 7 minus -5. -3 minus -7, watch out, that could be a tricky one, is +4. 7 minus -5, that one's easy, +12. Again, I'm going to reduce by dividing both numerator and denominator by 4, and I'm going to find that the slope of AB is 1/3. By the way, it also doesn't hurt to then graphically check that. If I came over to line segment AB, I could easily then see, right, that for every 3 units that I run, I rise 1 unit. So that slope of 1/3 makes sense. Let's do BC. All right, in BC, the slope is going to be 6 minus -3, all divided by 4 minus 7. Okay, 6 minus -3 is 9. 4 minus 7 is -3. And if I divide both of those by 3, I get -3 over 1. Or better yet, how about I just get -3 over 1. Okay, so what can I now say, right? Well, I can now say that AB is perpendicular to BC because their slopes are negative reciprocals. Therefore, angle B is a right angle. So, triangle ABC is a right triangle. Look at the logic there, right? These two sides, right, are perpendicular. Let me bring this picture up a little bit. So side AB and BC are perpendicular, and we know that just based on their slopes. Slope of positive 1/3, a slope of -3, okay? Because they're perpendicular, I can say that angle B is a right angle. Let me mark that, just so that you kind of see it on there. That's now a right angle. And because that's a right angle, triangle ABC is a right triangle. All right? And that's a very, very simple coordinate geometry proof. Don't get me wrong, the last one we did was also a coordinate geometry proof. All right? And they both involve the same thing, which is were two line segments perpendicular to each other. But this one got to a bigger picture, which is, can we then say something about that perpendicularity in terms of the triangle that we have plotted here? All right, let's wrap this lesson up. So in the first lesson of this unit, we saw that when two line segments have equal slopes, those line segments are parallel. Just as important as parallelism, though, is perpendicularity, when two lines or line segments form 90-degree angles. There, the slope relationship is more challenging. The slopes are negative reciprocals. So if one of them is 4/5, the other one is -5/4. If one of them is 7, the other one is -1/7. Okay? But using that relationship, you can solve a lot of problems that are very similar to the ones that we did with parallelism, right? Whether that's, sort of like finding out where two lines intersect, or determining whether a triangle has a right angle in it. Okay? Again, we're going to need this a lot when we get into things like squares and rectangles, in which right angles serve a very, very critical role. For now, though, I'd like to thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.